Hello, my name is Markus and I would like to explain the latest updates for GRAL. GRAL has been moved to .NET 8 and therefore some adjustments are required to start the applications. And there are numerous changes and bug fixes in GRAL. GRAL is now being released in two versions, the platform-independent version, and for Windows users only, there is a pre-compiled AOT, that means ahead of time version. What are the hints and advantages for the framework-dependent version of GRAL? GRAL and GRAM are running on Windows, Linux and Mac OS using the framework-dependent version. You need to install the .NET Runtime 8.xx, currently 8.0.1. You will benefit from security and performance updates of the .NET 8 framework. .NET 8 is an LTS long-time support framework and receives security updates for 3 years. GRAL and GRAM downloads are small. The application contains .pdb files so that precise information on program errors is available. Faulty virus scanner warnings are avoided. Virus scannings were reported for the large single file compilations that contained the entire framework. And you will get a better performance. And individual performance optimization is possible through user settings in the environment variables or the file gral.runtimeconfig.json or gram.runtimeconfig.json. Here are some hints for the graphical user interface, although there will be an own episode for the graphical user interface. The graphical user interface is running on Windows, a mono version for Linux is still provided. You need to install the .NET Desktop Runtime 8.xx and the other points are almost the same than for GRAL. The AOT version is a pre-compiled version for Windows. You do not need to install a framework. You will not receive any security and performance updates for the included framework. The download is larger. Only the graphical user interface contains a PDB file. You will get better performance for GRAL for some cases, and you will have a faster startup time. Here you can see results for performance calculations for several GRAL versions and GRAL settings. And in the next slice we see overall results. We can see that the dispersion is calculated much faster in the new version. This has partly to do with .NET 8, partly with performance optimizations and bug fixes, which we will discuss later. The flow field calculation is unfortunately slower, but at the same time the processor load during the calculation has been reduced. It seems that the changes in parallelization and vectorization in .NET 8 led to a regression in performance compared to version 22.09, which was compiled with .NET 6. Compared to version 19.01, however, there is still a performance gain in all cases. You can optimize the performance of the framework-dependent version by making adjustments to the gral.runtimeconfig.json file. In my test environment, I achieved the best performance with these settings: tiered compilation true, tiered BGO true, gc.server false. The AOT compiled version is using SSE vector extensions only and is therefore a little bit slower than the AVX vector extension used by the framework-dependent versions. This limitation might be caused by the AOT compiler, and we hope that it will be fixed in the next .NET version. Here we see the file gral.runtimeconfig.json, and you have the config properties that can be changed. In this case we see true for gc.server and false for tiered compilation and tiered BGO. I changed these values to true and gc.server to false for maximum performance on my system. You can also extend these settings. You can find a list of all possible settings at Microsoft by searching for .NET Runtime configuration settings. Then we need to talk about a problem reported by users, namely too high calculated concentrations next to the stack. In the Alaska dataset, we see measured concentrations in the vicinity of a stack with a high exit temperature and velocity at high wind speeds due to the stack and building downwash. GRAL overestimated these concentrations, so we tried to track the particles and to find out the reason for the high concentrations. However, the problems we found with particle tracking have nothing to do with the Plume Rise, but with the reflection algorithm. We found multiple reflections of single particles which caused several hundred, sometimes several hundreds of thousands loops within the reflection algorithm. Here we see an extreme example with 180,000 reflections within the reflection algorithm. This particle starts at 500 meters above sea level. This is an example with terrain, and is moved down to minus 3,300 meters by 180,000 multiple reflections. That was really a surprise. So we found an old program flaw within the reflection algorithm. The good news, we found no effect on the model results, but there is a negative impact on the performance, of course, and therefore we had to work on the reflection algorithm to avoid incorrect multiple reflections. And we got a performance gain in the dispersion part of the calculation by 10 up to 30%. But this bug has not yet fixed the high concentrations next to the stack. The background to this is that in some cases the algorithm cancelled the buoyancy too quickly in the first fractions of a second after the release, but in other cases the Plume Rise was calculated for a too long time. The change to the Plume Rise algorithm required numerous tests and validation calculations. I would like to show you a small part of this in the next slides. Here we see sections of the bloom in the wind direction showing the high on the y-axis and the distance on the x-axis. In this case, with a stack diameter of 1.5 meter, an exit velocity of 6 meters per second, an exit temperature of 100 degree, a stack height of 100 meter, and a wind speed of 1 meters per second at stability class 4, we see almost no difference, except that the Plume Rise algorithm ends earlier and the bloom therefore reaches the ground slightly earlier. Here we see a low wind situation in the latest version with a slightly reduced Plume Rise due to the limited wind fluctuation, which previously resulted in wind speeds of 0 for single time steps. In this example, we also see slightly higher concentrations near the ground due to earlier termination of the Plume Rise algorithm. And finally a case with a building and very high wind speeds, as in the Alaska dataset. Here we can see that the Plume Rise at the source is slightly higher in the new version, and the concentration in the building's downwash zone is reduced. But how are the validation datasets affected by these changes? We take a look to the Alaska dataset. The fractional bias is better and the normalized mean square error is also reduced with the new version. The quantile plots are almost the same at the first view. For the Denver-Julesburg dataset, we see improved values of fractional bias and normalized mean square errors and better results in the quantile plots. Other news. The result files are written in a separate thread. For very large projects, for example with very large domain areas or when using a lot of source groups, writing the zipped result files can take several seconds or minutes. Now the writing runs in parallel while the next wind field is being loaded or calculated. This brings an overall performance gain. The displayed stability class of the original meteorology was fixed when using a gram wind field, and the used memory is now released at the end of a calculation, even if the console or the terminal window is not closed. And particles moving very slow over a long period of time, or trapped particles, are removed. This modification can reduce artificial concentration peaks far away from sources and can increase the computing speed for large projects. Well, I hope you enjoyed this episode. Goodbye and have a good day.